Right. Let us go through this question. The time period of a particle in SHM depends on the force constant K and mass m of the particle. The time period is given as 2 pi root over of m by k. A simple pendulum executes SHM approximately. Why then is the time period of a pendulum independent of the mass of the pendulum? In case of spring, the spring constant is independent of the mass attached, whereas in case of a pendulum K is proportional to m, making K by m constant, and thus the time period comes out to be independent of the mass of the body attached. The motion of a simple pendulum is approximately simple harmonic for small angle oscillations. For larger angles of oscillation, a more involved analysis shows that t is greater than 2 pi root over of L by G. Think of a qualitative argument to appreciate this result. In reaching the result t equals 2 pi root over of L by G, we have assumed sin x by L equals x by L. This assumption is only true for very small values of x or theta. Therefore, it is obvious that once x takes larger values, we will have deviations from the above mentioned value. A man with a wristwatch on his hand falls from the top of a tower. Does the watch give correct time during the free fall? The watch must be using an electrical circuit or a spring system to tell the time, and therefore free falling would not affect the time his watch predicts. What is the frequency of oscillation of a simple pendulum mounted in a cabin that is freely falling under gravity? While free falling, the effective value of G inside the cabin will be 0, and therefore the frequency of oscillation of a simple pendulum would be 0. That is, it would not vibrate at all because of the absence of a restoring force.